Welcome back, class. I want to take today to talk about the practical side of the Industrial Revolution, one of the ways in which the Industrial Revolution physically changed one of the most basic aspects of our everyday life, and that is the introduction and the commercialization, if that's even a word, the commodization, the commercializing, whatever, you go double check me on that one. The marketing of electricity for common everyday use. So we talked in the last lecture, and this lecture is really piggybacking off of the lecture on the Industrial Revolution. The Industrial Revolution, I said, being perhaps the most significant event in modern history, and I said that it's the most significant event in modern history because it's the event that most affects our day-to-day life. And I said that the Industrial Revolution changes everything. Every aspect of life is fundamentally and radically altered from what we do on a day-to-day basis, as far as our job, as far as what we eat, as far as what we wear, where we live, all this other good stuff. Well, the Industrial Revolution also changes the sciences. We're going to see a marked difference. So we began one of the earlier lectures in this class. We talked about the scientific revolution. We talked about the shift from a Ptolemaic system to a Copernican system. We talked about some of the key figures behind that shift. We talked a little bit about their lives. Well, today we're talking about the history of electricity and how electricity came into common use. And I say that the Industrial Revolution affects the sciences because the sciences are affected now in that people are pursuing the sciences insofar as they can make money off of the sciences. So the real driving force in terms of the history of electricity, once we get into the 19th century, is going to be whether or not this can be used and billed to the public. Whether or not this can be consumed, whether or not this can become a part of this consumer society that we've talked about. And as we'll see, and as you'll see, because this will relate to your readings, when we talk about the War of the Currents, this is what's really at stake. There's a lot of money involved here. And so science becomes not just something that sort of gentlemen scholars do in their free time, but it becomes a full-time occupation that is driven by the consumer society. Okay, so let's talk about the history of electricity. Now, the history of electricity, like all of modern science, goes back to the scientific revolution. Specifically, the history of electricity has always been heavily influenced by the English tradition. It begins with an English scientist, William Gerber, who in the 16th century, I think around 1580, 1590, you have to double check me on that one. Gerber publishes a book on magnetism, publishes a book on magnets. Gerber, really interested in magnets, how they worked, why they worked. Now, magnets have always kind of been around in history. People writing about magnets goes all the way back to the ancient Greeks. But Gerber's one of the ones to give it a scientific treatment. He's one of the first to really sit down and analyze how they work, and was first to publish a scientific volume on how they work. But what also makes him interesting, he's one of the first in England to start writing about the natural sciences, he's writing about magnets, but in general, he's writing about the emerging field of geology, the study of the earth. And he's one of the first to sort of outline how this sort of research should be done. And the reason why he saw this as important is because up until this point, there's not a clear distinction, and we sort of talked about this when we talked about the Copernican revolution. There's not a clear distinction here at this time between science and other fields that we would consider unscientific, like alchemy, even occultism, this sort of thing, studying nature for its magical properties. And so Gerber is trying to separate what he's doing from what the alchemists are doing. So he's one of the first to start thinking about what we would refer to today as a scientific method. Now, there's a PowerPoint that's going to correspond with this lecture you can find on Blackboard. And on that PowerPoint, I have this quote that I'm about to read. So if you want to follow along with me, this is what Gerber has to say. Our generation has produced many volumes about the abstruse and occult causes and wonders, and in all of them, amber and jet, these are some of the types of materials that they were experimenting with. And all of these experiments, amber and jet, are represented as attracting chaff. They have what we would today call static electricity. So they have static electricity, which if you like rub something and you touch it against like a feather or some like light material, it'll stick to it. So this is what Gerber's talking about here. They're represented as attracting chaff, but never a proof from experiment, never a demonstration do you find in these writings. The writers only deal with words that involve in a thicker darkness subject matter. They treat the subject esoterically, miracle-mongering, abstrusely, mystically. They never actually deal with experiment. And because of this, Gerber says, they have no fruit to bear. What he's referring to is he's trying to pull the scientific community away from appealing to older texts, to older authorities, which was the tradition. This is tradition in philosophy and theology throughout the Middle Ages. If you were going to make an argument about something, you would make sure that your position is supported by the ancients, right? You would cite Aristotle and Plato and Aquinas and Anselm, whoever, right, in order to prove your point. But what Gerber's saying here is that what's happening in the sciences doesn't require that sort of proof. That scientists are doing something fundamentally different. And if we're going to be experimenting with, at that time, what he referred to as magnetism, if we're going to be experimenting with magnetism, we don't need to cite ancient authorities. Rather, what we need to do is to conduct experiments. And Gerber lists numerous types of experiments that ought to be conducted. So he's emphasizing this sort of empirical approach to science that would come to define it later on. Now, there's a really important invention early on in the history of electricity. Beginning in about the 17th century, you have this little thing called the Leyden Jar. The Leyden Jar. It's really one of the first conductors. It's a really nifty experiment. I can't remember who exactly, let me refer to my notes real quick. I can't remember who exactly creates the Leyden Jar. I probably didn't put it on. This shows how well prepared I am. Anyway, so the Leyden Jar, basically you can take, and you can make one of these yourselves if you want to. Just please don't kill yourself trying to do it. So you take any glass jar, like a mason jar type thing, right? We could take, you got like this mason jar, and what you do is you fill it up. Well, first of all, what you do is you line the inside and the outside with aluminum foil with metal. They would have used copper or zinc back then. And you also line the outside with aluminum foil or metal. And the glass in between it's going to act as an insulator. So you line the inside and the outside with metal. Then you fill it up with water and you put a cork on it. And you stick a copper line all the way through the jar into the water. And that line is being led to there's a German scientist named Otto von Guericke who creates these electrical spheres. They're referred to as Guericke spheres. Basically, it's a smooth ball of sulfur that you would rub cloth around, and basically the sphere would start to conduct static electricity. And eventually, if you rub the sphere enough, it'd be able to give you like a little shock. It'd be able to conduct, make a little static electricity jump. So you would connect this piece of copper wire to this Guericke sphere, and it would charge the Leyden jar. And the Leyden jar is basically an early conductor. you would charge it, it would send the electricity from the Gerke sphere into the water, and the Leyden jar would contain the electricity for however long. Now, it could only store so much. But the Leyden jar, people in the 18th century, in the 17th century, sorry, people in the 17th century thought this was extraordinarily fascinating, but they weren't quite sure how this worked, because they weren't quite sure what electricity was. A lot of people believed that it was a fluid, but they didn't know, so they knew about positive and negative charges, right? So the early idea is that you have two different types of fluids. They didn't know anything about electrons yet, so they thought it was like a type of fluid, kind of like we think of water as a fluid today, that flowed through solid objects and was able to be transferred from one object to the next. And this is where Franklin comes in. Benjamin Franklin, one of the founding fathers of America, made a pretty important contributions to the theory of electricity, in that he's going to sort of unite the field under this one fluid theory in electricity. Franklin's going to argue that electricity is a fluid that flows through objects, that it sort of emanates from the earth. This is where you get Franklin's famous lightning experiment, where he ties the copper wire to the kite, and to the kite he attached some heavy copper keys, and he flies it in the middle of a thunderstorm, and the lightning strikes it, right? And he has it attached to a Leyden jar so it stores some electricity. Probably never happened. You can conduct the experiment today if you want to. Well, I take that back. You probably shouldn't, because, well, we actually don't, I say that probably didn't happen because we don't have any record of Franklin ever doing this, but we actually do have a record of a Frenchman conducting the experiment after he reads about it with Franklin, and of course he's holding on a copper wire as lightning strikes it, and it kills him. So I take that back. You don't do that experiment. So Franklin's important because he introduces this one, he introduces this idea of electricity as a fluid. Now, of course, that's wrong, but it's going to spark research into the area. Next up, and most notably, we have Galvani and Volta. Galvani and Volta. Galvani is going to be mainly interested in anatomy. Galvani, living in the late 18th century in Paris, I believe. Galvani is doing anatomy experiments, dissecting, this sort of thing. What gets him interested in electricity is a pretty interesting story. So Galvani explains this himself. He says that there was a time in his lab where he was dissecting some frogs. Can't remember the exact reason behind this, but if you ever taken an anatomy class, if you've ever dissected a frog, you can see Galvani has the frog kind of filleted, its parts are open so he can look at it. He's examining the frog's muscles, and he has the frog lying on a metal plate. And Galvani recounts the time where he's taking the scapula to cut into the frog's leg muscle, and a spark shoots from the scapula into the frog's leg, and the frog's leg kicks. Right? The scapula sends a small static charge into the frog's leg, and it briefly animates the frog's leg. Now, Galvani thought this was crazy, thought this was interesting. Right? He wanted to figure out what exactly was causing this. How did this work? Why did that happen? Right? The frog's dead. How could it move? So he creates this really elaborate experiment. He goes home, and if you can kind of picture this in your mind, he brings a lot of these frogs that he has in his lab, and he runs a wire connecting, I don't know quite how he did this, but he ran a wire, he stuck the wire through the frog's mouth, out its rear end-ish, yeah, that went through the frogs, that connected to the frog's spinal cord, and he put several dozen of these frogs on this long wire, because Galvani thought that somehow there are either two things going on. Either electricity was coming from without, that it was coming from perhaps the atmosphere, or it was coming from the frog's body itself, that something within the frog was producing electricity. So he puts them on his back porch and he waits for like a thunderstorm to see if the frog would be shocked and be moving around. It doesn't happen, so he brings the frog inside and he does the same thing, and that same thing happens with the spark. And so he concludes that the electricity must be coming from the frog's body, that this is what's making the frog move. Now, of course, he's wrong in the sense that the electricity is not coming from the frog, but it's coming from the metal, but he's right in the sense that this is how muscle contraction works. If you take an anatomy class and you talk about how muscles contract, if you see the arm muscle, right, it has to do with an electrical impulse sent from your brain to your arm that tells your muscle to contract. But Galvani didn't know any of that. But Galvani believes that he knew that, and so he comes up with this idea that sort of the animating principle, what makes people move around, what makes animals move around, is that we all have this like a small amount of electricity coursing and flowing through us. Now, electricity has been one of these areas of science that has been prone to showmanship. You get people with these like electrical devices that will like gather a crowd before them, and they'll do basically the equivalent of like magic tricks. And Galvani is one of these people. He would invite people to his lab. He's like, come look at this, come look at this. And then he would like shock the frog and it would move and people would flip out again. This is before like Netflix or Hulu Plus. This is like their only form of entertainment. Okay, so you gotta kind of put yourself in that mindset, right? Either, you know, you go to work and you're busting your back all day and somebody says like, oh, I can reanimate a frog, want to come see it? That's pretty exciting stuff. So Galvani was attracting some crowds. Now his cousin is the notorious showman who would do these experiments but on a much larger scale. And this is all hearsay. We don't actually have an account of him doing this. But apparently Galvani's cousin, who also had the same last name, I don't remember his first name off the top of my head, but apparently Galvani's cousin did this on a criminal that had been recently executed. The criminal had had his head chopped off, and Galvani's cousin ran up there and like shocked his dead body, his corpse, with an electrical charge, and apparently the corpse like moved around and people like lost their shit. Like it was just the craziest thing that they'd ever seen in their lives. And this is actually the inspiration behind Mary Shelley's Frankenstein. This is why you get the Dr. Frankenstein, the mad scientist. This is why he's like trying to channel the lightning and put the electricity into the dead body, because it's believed that the electricity is what animates us. That's the idea behind that. Okay. Volta is writing after Galvani and fundamentally disagrees with what Galvani has to say. Volta doesn't buy this whole animal energy type thing. So Volta is going to try to figure out where exactly this charge is coming from. And Volta's famous because he essentially builds the first battery, a Volta Stack. Basically, if I can, you'll have to excuse my art skills. There's a reason why I flunked out of art school. So he's got like this metal plate, and he's attaching plates of zinc, or I think it's zinc or sulfur, these round plates, and in between these plates, this area here-ish, he has these wet pieces of cardboard that he has soaked in salt water. And so he stacks these plates on top of these pieces of cardboard, and then he sends an electrical charge through it. And what he found is that not only did the electrical charge go through it, but that the electrical charge kept. It's not like a Leyden jar. A Leyden jar, people do all sorts of crazy experiments with Leyden jars. There's an experiment of this monk that's really into Leyden jars. So he builds this huge Leyden jar, and he gets all the monks of the monastery to hold hands, and then using the Leyden jar, he shocks one, and it sends an electrical charge through all the monks that are holding hands. They all get shocked a little bit, and they're all like, oh wow, that was great. But a Leyden jar is like a one and done type thing. It emits a charge and that's it. Then you have to charge it again, right? But what Volta found with his stack is that once it was charged, you could keep getting a spark from it. Every time you touched a copper wire to it, it would emit a spark. This went on for a while. So Volta Stack was able to hold that charge for longer, and this showed Volta that the electrical charge that was being emitted from Galvani's frog wasn't due to some sort of inner electricity of the frog. Rather, it was due to some of the conducting metals that was perhaps touching that Galvani didn't realize. Okay, all of this is sort of building up to the 19th century. And in the 19th century, once these little experiments are becoming more and more powerful, once the electrical charge is being stored up, it's becoming more and more powerful, people start to realize, well, maybe we can do something with this. Maybe we can use this, excuse me, maybe we can use this as an alternative form of energy. In 1799, the Royal Institute is created in Great Britain. And the Royal Institution is created for the purpose of advancing industrial technology. I'm going to read you another quote. Again, I'll put this on the slide so you can read along with me. The Royal Institute, created in 1799 by Count Rutherford's somebody different that we'll talk about. Count Rumford. And the Royal Institute is created for this purpose, and this is a quote. This is kind of like their statement of purpose, their motto. The Royal Institution is created for diffusing the knowledge and facilitating the general introduction of the useful mechanical invention and improvements, and for teaching by courses of philosophical lectures and experiments the applications of science to the common purposes of life. Now, Rumford was a very practical man. He spent some time overseas maintaining and working with various armies, trying to create an efficient army as terms from like a logistical point of view. So he comes back to England, and the Industrial Revolution by this time is in full swing. And so he's seeing the emergence of all these new technologies, and he realizes that he needs to create a school in order to train people, not like a traditional school. A traditional school you would go to and you would learn to read Greek and Hebrew, and you'd read the Bible and other classical works of literature. But Rumford looks at what's happening and he says, well, we don't need to be training people in Greek and Hebrew. We need to be training people to figure out how to develop new machinery, how to come up with new techniques. And he saw electricity as kind of the prime example of that. And it's because of the school that we have some of the greatest electrical scientists and some of the greatest scientists, period, in history, Faraday and Maxwell. Faraday is actually comes from a very poor family, and from a very young age, gets an apprenticeship at a bookstore, binding books, creating books. And in his meantime, he's reading a lot of these books. One of his favorite books to read is the Encyclopedia. And so he's reading about these new findings in the field of electricity. And Faraday happens to live in London and happens to live within relatively close proximity to the Royal Institution. And he sees that the Royal Institution has been created, and by the time that Faraday's a young teen in his early 20s, that they're offering free public lectures, because part of the purpose of the Royal Institution is to educate the public, to find people that perhaps want to get into this field. And Faraday, as this young, bright intellectual, goes to several of these lectures concerning electricity. Eventually, he's able to talk his way in. The head of the institution at the time is a man named Davies. He's able to get an apprenticeship under Davies, and Faraday proves to be one of the father of electromagnetism. Creates the first electrical motor, very simplistic motor. It's probably not what you're thinking in your head, but if you want to go look it up, it's pretty interesting. Faraday comes up with several hundred of different types of experiments to prove electromagnetism. One of the first to do work on electrical fields. And Maxwell is sort of the mathematician behind this. If you ever go into engineering, specifically electrical engineering, you'll need to know Maxwell. Fortunately, we don't have much time to spend on these two, and it's way above my pay grade anyway. I wouldn't be able to explain it if I wanted to. So instead, we're going to skip to the War of the Currents. And the War of the Currents refers to it was really not really a competition. It refers to a struggle that takes place between Thomas Edison and the Westinghouse Corporation, which had employed Nikola Tesla. But this is happening in the late 19th century America, specifically New York City. Thomas Edison is probably one of the foremost American inventors. Some of the other different types of technologies that I mentioned in the lecture on the Industrial Revolution, the telegraph, this is where Edison gets rich from at a very young age, is improving and working with the telegraph. Once Edison makes a small fortune when he's relatively young, he establishes what is perhaps, I'm pretty sure, is the first industrial / research lab in America, anyways, in New York in Menlo Park. Edison uses his own money to build this place, and Edison kind of switches gears because electricity, by Edison's time, we have the mathematics, we have the science behind it, but no one had quite figured out how to make money off of it. And there are some major problems standing in the way. There are two problems standing in the way. First and foremost, no one knew how to power, I back up a little bit. So we have light bulbs at this time. No one knew how to power these light bulbs or sustain power to these light bulbs. Sure, we could get enough electricity from one of Volta's batteries to power it maybe for an hour. That was about it. And we have the beginning of generators in the 19th century, but there's no power grid like we have today, our power grid today. So Edison, that's the first problem, is the problem of power. The second problem is with the light bulb itself. Edison is going to be the first to invent a fluorescent light bulb, or incandescent light bulb. Incandescent light bulb had already been invented. Edison is going to improve upon the incandescent light bulb because all of the light bulbs up until this point they were only powered for about an hour, only capable of being powered for about an hour, only lasted a couple of hours at most before you needed a new light bulb. So economically speaking, this wasn't really a viable option. Most people at the time used gas lighting, and if you look at a picture of New York City from the mid-19th century, the street lights are all gas lights. So Edison has two problems to overcome. First is the issue of power. Second is the issue of creating a sustainable light bulb. And it's at his laboratory at Menlo Park that he's able to overcome both of these. First, by inventing a light bulb that could hold a charge for several hundreds, if not thousands of hours, making it feasible to sell to people cheaply. And second of all, by creating the first power grid. So Edison invests in these generators using DC current, using direct current. They would send a very low voltage through underground lines. Edison spent a ton of money investing in this basic infrastructure of building the power plant, and then from the power plant sending it to what would eventually be people's homes, using low voltage direct current. And so this is what skyrockets Edison to fame. But within 5 years of Edison doing this, he has this big reveal. So he invites the mayor of New York, he invites the gentleman that was in charge of maintaining the gas street lights, he invites them to his laboratory, and there's this elaborate ordeal you can read about. We have first-hand documentation, there's several reporters there. Edison invites them all just as the sun is going down, and so it's the winter time and they're all standing there in snow. And so they're just waiting for Edison, and finally Edison walks out and he hits the switch and these lights come on. And again, you have to remember people aren't used to seeing light bulbs back then. at least not on a regular basis. So these lights come on, and it just like dazzles people. But not only that, Edison has them on like a delay switch. And so the lights are coming on and off, the first Christmas lights. And people are just like dumbfounded. So Edison immediately gets a contract with the city of New York. And the city of New York wants to test to see if electric light would be a viable alternative for gas light. So Edison gets this contract, and by contract we're talking about a couple of $1 million by today's standards, right? They really see the potential of this. Well, another company, Westinghouse, catches wind, and they see a business opportunity. Now, back up a little bit. Nikola Tesla, in his younger days, works for a sub-company that Edison has in Paris, France. They realize Tesla's genius. They quickly send Tesla over to America. Tesla actually works for Edison for a bit. And the story goes is that Edison had a generator that needed to be fixed. Tesla kind of steps up and says, yeah, I can fix your generator. In fact, I can fix just about anything here. And Edison says, oh, okay, all right. Well, I'll tell you what. You fix my generator, I'll give you $1 million. Tesla says, no problem, piece of cake, right? So Tesla actually goes and fixes this massive generator that Edison has, comes back, and Edison's reportedly, right? Edison said, no, I meant that as a joke. Whether or not it was a joke, we don't know. Either way, Tesla gets pissed off at this and leaves Edison's company. Well, after he leaves Edison's company, another major company, Westinghouse, picks up Tesla. And the reason why they pick up Tesla is because they hear that Tesla understands and knows how to build an AC generator, an alternating current generator that is more efficient than a DC generator. So it's actually a pretty interesting story. After Tesla quits working for Edison, he quits working for Edison in the capacity that he was, and in order to get work, he's actually digging ditches for these underground lines. And as he's digging ditches, he starts talking to people. Anyway, somehow he gets into contact with a representative from Westinghouse, and they bring him in. And they get Tesla to build one of these alternating current generators. Now, the issue facing Edison's generators is that direct current, which means a steady stream of electricity, is flowing from the generator, the place producing power, to where it's being used, the street light, for example. So the problem with this is that, first of all, you have to have a constant stream of electricity going. Second of all, due to the type of wire that they used, the direct current could only go so far. And eventually it would lose its charge, it would lose its steam. Tesla's AC generator didn't have that problem. And in fact, it could operate at much longer distances. And what this allowed the Westinghouse company to do is that it allowed them to build generator sites outside of the city, therefore for cheaper, much larger sites, because the land was cheaper. And basically, Westinghouse is able to do what Edison is able to do, just at a much cheaper cost. And so they start to undersell Edison. And eventually, within time span of less than 10 years, are basically able to run Edison out of town. And there's a whole lot of other, Edison, of course, doesn't take this lightly. In fact, kind of makes him kind of go crazy. And you'll read about this in your reading, but this is a pretty vicious business cycle and that goes into this. Anyway, if you have any questions about the reading, feel free to email me. If not, I'll see you guys next time.